Hello, I'm Kiran Kumar from Nature of Physics. Today topic is potential energy of the spring. Please do like and subscribe our channel Nature of Physics. Full video watch student, then you will get clarity. See student, considering a spring of force constant K, this is the spring constant K or force constant. One end of the spring is fixed to a rigid support, this is the rigid support fixed, and other end is connected to a block on the smooth horizontal surface. See student, here there is no applied force, that's why there is no elongation in the spring. And second diagram, a person is pulling with a force F, applied force student, that's why along the direction of force the block get the displacement is x, so that is taken as elongation of the spring. And restoring force, elongation, both are in opposite direction student, and applied force and elongation in the same direction. So here O is the main position, P is the position is represented there, elongation position, so that restoring force is directly proportional to the elongation in the spring student. So restoring force Fr is directly proportional to the elongation in the spring, and equal in magnitude and opposite in direction. Minus represent the opposite direction. Fr represent the restoring force, F is the applied force. Here restoring force, applied force both are equal in magnitude, opposite in direction, that is equal to Kx writing, because of Fr directly proportional to minus x, and Fr is equal to minus Kx student. K is the proportionality constant, that is K, spring constant I gave you already. See, F applied force and F restoring force both are in opposite direction, that is equal to net force student. F minus Fr is equal to F net. If F net force is equal to 0, F minus Fr is equal to 0 writing student. So I am getting F is equal to Fr student. Already we got this equation, Fr is equal to minus Kx, same only I wrote. Even F also minus Kx student, because of we got F is equal to Fr student. So applied force is equal to restoring force. So next derivation is small work done by the restoring force. So small work done is dW student, so that dW which is equal to Fr bar minus dx bar student. See that, notice that point here, Fr and dx both are in opposite direction, Fr left side and dx is right side, represented in the diagram clearly. Okay student, and theta is equal to 180 degrees cos 180, which is equal to minus 1. So dW which is equal to Fr dx cos 180. So dW which is equal to Fr value is minus Kx into dx into cos 180 is minus 1. This minus is get cancelled. Finally I got dW is equal to minus Kx into dx. This is small work done student. Okay, and we need to find the total work done. So next I am going to write the total work done student. Total work done, that is integration on both sides, integration on both sides the above equation. So integral dW which is equal to integral k into x into dx. So integral dW is equal W student, which is equal to k common constant, and integral x to the power of 1 into dx. Okay, so W which is equal to k into integration x to the power of 1 into dx, which is equal to x to the power of 1 plus 1 by 1 plus 1, basic formula using student. Okay, now W which is equal to k into numerator is x square, denominator is 1 plus 1 is 2 student. So that work done which is equal to half into kx square writing student. So I can write this is the first equation, Fr is equal minus kx and F is equal to minus kx, also writing equation number 2 student, and this is equation number 3. But here work done which is equal to potential energy of the spring U. See, work done is stored in the form of potential energy of the spring. So W is equal to U student. Now U formula which is equal to of kx square, already given here also. This is I can write as equation number 4. So that is first page and this is the second page. In the second page we are going to find the work done by the applied force. Previous pages give the work done by the restoring force student. So K is the spring constant, this is the mean position O representing, and next a person is pulling by a applied force F student. That's why the spring get elongation is x1 from the mean position, clearly given in the diagram. Restoring force is opposite direction to the elongation, and two persons is pulling in the second diagram. That's why applied force is increases student, then restoring force also increases, and here elongation is taken as x2 student. And third diagram is given, just example for the second diagram student. In this compression is taken x1, elongation is equal compression for the second diagram only student. See here elongation is x1 is right side and restoring force is left side for the second diagram. Similarly fourth diagram also considering representing with respect to second diagram only. Here restoring force is acting right side student for compression, and compression is acting left side. Here also restoring force and compression distance both are in opposite direction. Always restoring force is opposite direction to the displacement. Okay, so this is the second diagram in which elongation taken, and this is the third diagram taken, that is taken as what is that student? Compression. Okay, so that there is a small work done by the applied force. Applied force formula proof already I gave you in the previous page. F is equal minus kx student. Small work done by the applied force, so I can write dw is equal to small work done which is F applied force dot dx bar. Dx bar is the small displacement in the direction of elongation taken student. So one thing we have to notice student, here applied force F and displacement dx both are along the same direction, theta is equal to 0 student. So that dw which is equal to F into dx into cos 0 student. Cos 0 is equal to 1, so that dw is equal to F into dx into 1 student. Now I wanted to replace here F value. F value is equal minus kx student, so that dw is equal to minus kx into dx. So this is the small work done student, but we have to find the total work done. Total work done is from x1 elongation to x2 elongation we have to find. So clearly written total work done from x1 to x2 student. That's why integration on both side. Okay, integration on both side, integral dw which is equal to minus k into x into dx student. Here minus kx is constant common, so that integral dw is equal to w student, so that minus k into here x to the power of 1 is there student. That's why x to the power of 1 plus 1 divided by 1 plus 1. Okay student, and limits also replacing here 0 to, sorry I forgot to write the limits. Limits are x1 to x2 student. Here this is lower limit is x1 and upper limit is x2. Okay, so w which is equal to minus k into x square divided by 2, lower limit x1 and upper limit is x2. So w which is equal to minus k into upper limit is x2 square by 2 minus lower limit is x1 square by 2 student. Upper limit x2, lower limit x1. So upper limit minus lower limit value replacing according to the formula student. So that w which is equal to minus k divided by 2 x2 square minus x1 square, and w which is equal to minus half into k x2 square minus x1 square, student. Okay, continuation steps also we can write there. W which is equal to minus half k x2 square minus of minus plus of k x1 square, student. Okay, and then w which is equal to, we will get, this is minus u2 and plus u1. Due to the x2 elongation, potential energy of the spring is u2. Due to x1 elongation, potential energy is u1. And also we can write w is equal minus common u2 minus u1. This is clear information about the elongation of the spring. Due to the elongation, here spring has the potential energy. So work done by the restoring force and work done by the applied force, both we got, student. Relation also clearly given. Thank you. And here equation also representing here, this is equation number 1 and this is equation number 2, student. So please do like and subscribe our channel Nature of Physics.